Yes, back to trigonometric identities. And we've seen identities before. For example, if you have a difference of squares here, x squared minus 25, this x minus 5 times x plus 5 will always be equal to x squared minus 25. It doesn't matter what I make x. I can test different values of x and see if that's true. So let's try one. Let's try x is 0. So I have 0 minus 5 is minus 5. And 0 plus 5 is plus 5. Minus 5 times plus 5 is negative 25. And then over here, I would have 0 squared is 0. Minus 25 is minus 25. So that's true. And then I might test a different value. Let's try 5. 5 minus 5 is 0. 0 times anything is 0. And I have over here 5 squared is 25. 25 minus 25 is 0. So they're the same. Right? And I can show that they're the same for a variety of different x values, but that's not exactly proving that they're the same. I can prove that these are the same with algebra by factoring x squared minus 25 as a difference of squares, and then I do get x minus 5 times x plus 5. Okay? So that's one example of an identity. We can replace one side of the equation with the other, and we still have the same value. So here are the steps that you're going to use to solve trig identities, and these are on your handout. If you don't have your handout, it's at the front corner. So the first thing that we need to remember to do with trig identities is they're not like equations where we're going to be moving things from one side to the other and dividing by something and multiplying by something. We're actually going to work with both sides of the equation separately. And we want to do this because until we've proven it's true, we don't know that it's an equation. We don't know that they are equal. Once we prove that they're true, then we can work with them more like an equation. Okay? So it's easier to work with the larger side and convert everything to sines and cosines. This isn't the only method, but it is our preferred method, is to convert everything to sines and cosines and use all of your mathematical concepts to simplify it. You can factor things. You can use fractions and work with creating common denominators. You can use identities. You can multiply by 1. You can subtract 0. You can do these types of things that will allow you to manipulate it and change it. And then if your left side is still not equal to the right side, then start working on the right side until you can get them to equal each other. And once you're done, once you've worked one side so that it's identical to the other side, or you can work both to the identical place, then you say left side equals right side, therefore it's true. So let's take a look at, just to remember, like here's a bit of a paragraph from one of my predecessors, so let's read it out. Proving trigonometric identities, it's like solving a puzzle. It really does tickle the mind. It can be a great topic. It'll make you think logically and creatively, applying some of your mathematical knowledge to unlock these puzzles. You and the next person, you might have very different ways of solving different trigonometric identities. Some of you might take a very long road. Some of you might be able to do it in just a few steps. One is not better than the other. It's just to get in there and start working and start proving some of these ideas. So your job when you're working on these is to show that the left and right sides are the same. If you can, then you've completed the proof. So there's 3 different types of trigonometric identities that we'll use. The first are the reciprocal identities, and we've seen these before, so we'll review those. There are the quotient identities, and then there's the Pythagorean identities. It says here we've seen the quotient identities already, but I don't think we did. I think that's something that we need to take a quick look at. But the Pythagorean identity is new. But as you can guess, a squared plus b squared equals c squared. This is related to opposite, adjacent, and hypotenuse. And that makes it actually fairly easy to remember, especially if we review the unit circle today. So let's take a look. This says it won't be provided to you on your test or exam. Remember when we used to have exams in classes? Like you all had grade 9 before COVID, right? Or was first semester of grade 9 you wrote exams and then you haven't written exams in high school? Oh my goodness. How then are we going to reinstate them for your grade 12 year? You this generation might have like the biggest like whiplash if that does happen, if we do exams again next year. Just something to think about. Wow. Okay. Yeah, anyway, so let's take a look. Our reciprocal identities, I'd like people to take these down. And this is mostly review of just what these definitions are. And so you'll find that you have a space for them at the bottom of your page there. I've written the sine, cos, tan. If I tell you sine x, well, I can write sine x in another way. I could write that as 1 over cosecant x. And cosecant x, well, I could write that as 1 over sine x. I can freely flip these things, no problem. That's always available to me. And that's just a definition. These are how these reciprocal trigonometric identities, cosecant, secant, and cotangent, are defined. Remember, there's a neat trick to remembering which one goes with which. Sine goes with cosecant because this one has a co, and each pair has a co in it. Secant goes with cosine because it has a co. It's over there. And then tangent goes with cotangent because of course it does. They're both tangent, and here's your cotangent. Okay? So that's how you remember which one corresponds to which one. Okay. Now there's another thing to think about with these. Sine x, well, I can also write sine x as opposite over hypotenuse. So that means cosecant x is hypotenuse over opposite. If that's not immediately apparent to you, then this is something that's very useful to remember. If I just flip the trigonometric ratio, then I get the reciprocal one. So cosine is adjacent over hypotenuse because SOHCAH, S-O-H-C-A-H. Then secant would be hypotenuse over adjacent. And then tangent is TOA. Tangent is opposite over adjacent. So cotan is adjacent over opposite. Just flips it. Oh, let's keep going. Oh, and then another neat thing to remember is that the square of each ratio is equal to the square of the reciprocal. So if I'm looking at secant squared x, that's equal to 1 over cosine squared x. Just I can square both sides of the equation, and they're both still true. If I square something like 1 over cosine x, if I square secant x, I just get secant squared x. But if I square this, it's top times top over bottom times bottom. 1 squared is 1. So that's why it's still 1 over cosine squared x. Okay? That's just squaring both sides. But we don't usually write 1 squared. That's a very strange thing to point out, that this is 1 squared, not just 1. Okay. Now let's keep going. All right. So now the quotient identities, it actually turns out that tangent is actually sine divided by cosine. Okay. And we can prove this is true. Let's take a look at the unit circle. The unit circle looks like this. You may want to sketch a unit circle here just to recall. And it's a circle with radius 1. And it so turns out that the value of any point on this circle, if this is here a radius 1, that this point here will be given by, if this is theta, angle theta, then this will be given by cosine of theta, comma, sine of theta. Because this is a radius 1, and if I look at the opposites and adjacents that create that, well, here, sine is given by, here, this angle here. Sine is opposite over hypotenuse, but the hypotenuse is 1. So this opposite side will just be the value of y there, how tall this is just given by sine theta. The adjacent here, this is the x value of that point. And the x value of that point, well, it would just be the adjacent over the hypotenuse of this angle, which would just be given by cosine theta. And this is how, when we do some kooky animations in Desmos, let me get a fresh Desmos here. I've been playing a lot with Desmos, building you these challenge problems. And if I get my face out of the way, I can open up. Here is the trigonometry unit circle. So the way they create this unit circle here, notice this point, cosine of A, sine of A. That's this point right here. And as I change the angle A, it just tracks and follows that circle all the way around. Doesn't matter where I stop it. Here is 278 degrees all the way around to there. And the value of the y is down there very close to -1. That's because sine of 278 is very close to -1. If we have sine of 270, you'll recall that's the minimum value of sine down there at -1. And that's where we have -1 equals sine. So that's the point 0, -1. So that's just is that point, and it's determined by that angle. And that's how I was able to make this terrible brain torture here, where you just take the value of cosine A sine A, and that's you going around a Ferris wheel. Okay, turn that off so that it doesn't consume a lot of computing resources. Leave. Okay, go back to the lesson, Mr. Jennings. Okay, unzoom. So if that point is cosine theta sine theta, well then tangent will be opposite over adjacent, but opposite is given by sine theta, and adjacent is given by cosine theta. So I can say tan x is equal to sine x over cos x. It just is. It's by definition. But I could also work this out by converting back to opposites, adjacents, and hypotenuses. So watch this. Tangent tan x is equal to opposite over adjacent. That's the left side of this identity, tangent x. Let's work on the right side separately. So here's the right side. I'm just going to remove my unit circle because I'm going to want that space, despite how beautiful a unit circle that was. The right side is equal to sine theta, sine x, over cosine x. Now let's write that out as opposites and adjacents and hypotenuses. Sine x was opposite over hypotenuse, and cosine x was adjacent over hypotenuse. Now when we divide by a fraction, we just need to flip and multiply. So that's equal to opposite over hypotenuse multiplied by hypotenuse over adjacent. Notice that the hypotenuses cancel, and we get opposite over adjacent. Because therefore left side equals right side. So that proves that this is true for all angles x. Notice that that's now been shown algebraically, as well as with ideas from the unit circle, as well as with if I divide a sine curve by a cosine curve, I'll get a tangent curve. Okay, I could do that with functions as well. Now the opposite is also true because cotangent's the reciprocal of tangent. So that one I just need to flip cosine x and sine x, and that's also true. It would prove in exactly the same way. We just end up with adjacent over opposite there, and cotangent is adjacent over opposite. So we can continue. Now, the Pythagorean identities. This one is the main one. This is the one that you want to remember. Okay? That's the equation of the unit circle. X squared plus y squared equals r squared, where x is given by cosine squared, and y is given by sine squared. So that's the equation related to the equation of a circle, but it's also related to the Pythagorean theorem if my hypotenuse is 1. Okay. So yeah, that should make total sense. And well, let's take a look at an example with a triangle here. So here's a triangle. I'm going to claim that this is an angle x, this is a hypotenuse of 1, and this is a right angle. So in this case, this is the opposite side. So the opposite over 1 would be equal to sine x. So this side is just sine x. And then this would be cosine, because this is the adjacent. So this side is given by cosine of x. So cosine x over 1 is the value of cosine of x. And if I square these two sides and add them together, it will equal this squared. So sine squared x, that's this one squared, plus cosine squared x will be equal to 1 squared. And 1 squared is a really fancy way of saying 1. So we don't usually say 1 squared, we just say 1, because 1 times 1 is 1. So that's true. Notice the way you write down sine squared x. It is not the same thing as saying sine of x squared. This would mean square this angle, multiply this angle by itself, and then evaluate the sine of that number. So if you did say want to take like sine of 30 and then square it, That would mean you'd take 30 times 30 and you would get 900, and then you would find the sine of 900, which would be a weird thing to do. That's not what we're doing here. What we're doing is sine squared of x. That means evaluate what sine x is first and then square the result. So the sine of 30 is 1/2. So sine squared 30 would be 1/4. And that's how you do that. Okay. And now, these ones, 1 plus cotangent squared x is equal to cosecant squared x, and tangent squared x plus 1 is equal to secant squared x. Okay, these are other identities. They're the first time I've seen them written down as identities. I only work with this one, and I work my left side and right side until I can use this. But apparently these ones are the same. So let's take a look at those, and we could evaluate them as identities as well. So we'll come back to that. I want to go through these examples that you have on your page. So anyway, here's how we would start working on an example like this. We've been asked to prove that this is true. Okay, so let's do that. First thing we do is start working on left side or right side. So let's start on left side. And we're going to start with tan x plus cotangent x. I'm going to write these as expressions of sine and cosine. So tan x is equal, so I'm just going to write it down again. Tan x plus cotangent of x. All right. Now tan x, that's equal to sine over cosine, opposite over adjacent. So that's equal to sine x over cosine x. And then I'm going to be adding that to cosine x over sine x. Now I just want to add these two together. And when I'm adding fractions, what do I need on the bottom? Yeah, I need a common denominator on the bottom. So what I'm going to have to do is multiply both of them, top and bottom, so that I do get that common denominator. I'm going to multiply this one by 1. So I'm going to multiply by sine x over sine x. And this one I'm going to multiply top and bottom by cosine. Cosine x over cosine x. And let's do that. Now, we get that common denominator we need to add them together. Here I would get sine x times sine x. That's another way of saying sine squared x. All divided by sine x cos x. But that's the same denominator I have over there. So I can actually extend that fraction and say that that's sine squared x plus cosine squared x. So I find sine squared here, I find cos squared there. Because they're over the same denominator, the pizza is being cut into the same number of slices. So I put that denominator together on the bottom. It's the same. And so I have sine squared x plus cosine squared x over sine x cos x. Aha! Now I recognize sine squared x plus cosine squared x, that's equal to 1. So let's write that down as 1. Okay? So that's equal to now 1 divided by sine x times cos x. Okay? I don't know how to make that any simpler. I can't make that any simpler, so I leave it there. Cool. Now, let's work on the right side. It still doesn't look exactly like that, does it? But it is. It's exactly the same. Okay? Secant x multiplied by cosecant x. Well, secant x, that's just equal to 1 over cosine of x multiplied by, well, cosecant x, that's just 1 over sine x. And when multiplying fractions, I do top times top over bottom times bottom. So look at that. This is equal to 1 over sine x. Because multiplication is commutative, I can write this in any order, so I might as well write it in the same order over there so my audience is not confused. Sine x times cos x. Left side equals right side, and I can say therefore left side equals right side, therefore this was true. Therefore tan x is cosine, therefore this is true. Okay. See how I worked the left side independently of the right side and made them equal to the same thing. That's the name of this game. Dave. What do you mean why is sine the opposite? Oh, when I write down tan x here, and it's opposite over adjacent? Well, that's one of the identities we've been given tan x is equal to sine x over cos x. And I can show that in a couple ways. I can show that with a unit circle where the hypotenuse is 1, then the value of the opposite is sine x. That sine x times 1 is sine x. And then cosine x down there will make that triangle. But I can also write tan x as opposite over adjacent. And then I can write sine x as opposite over hypotenuse and cosine x as adjacent over hypotenuse. When I flip this and multiply, the hypotenuses cancel, giving me opposite over adjacent. Therefore, tan x is equal to sine x over cos x. Okay, so there's a few ways that I can prove that. Because I can prove it once, I can use it again and again and again. And that's one of those pieces that when a mathematician is looking at you proving trig identities, they will accept that tan x is equal to cos x over sine x. Sine x over cos x. They won't question that. They won't say, wait, how did you get that? So that's one that we can just use. Let's take a look at another one. 1 minus cosine squared x is equal to sine x times cos x times tan x. Let's try this. Okay, first of all, I could start by I can look at that and tell you that that's sine squared x. How can I do that? Well, let's do the math and we'll work on it and we'll find it. But I can also, I would use a trick here because I know sine squared x plus cosine squared x is equal to 1. I know if I subtract cosine squared x from both sides, I get sine squared x equals 1 minus cosine squared x. But let's say I didn't know that. Let's say I didn't know that as an identity. It's just one inverse operation away from that. But let's say I didn't know that as an identity, and I wanted to prove that this is just sine squared x. Let's work on the left side here. It's 1 minus cosine squared of x. So let's write this out as let's write 1 out so that we can get it with a common denominator. Wait, it's not common denominator. Yeah. So if I wrote 1 as, well, how can I do that? Thank you. So what I would need to do here to prove that this is true without going through the trigonometric identity is write these as opposites, adjacents, and hypotenuses. So if I say 1 minus cosine squared x, well, cosine is adjacent over hypotenuse, but I was asked to square that. So that's cosine squared, is adjacent squared over hypotenuse squared. Now, let's write the 1 as hypotenuse squared over hypotenuse squared. So this would be h squared over h squared minus a squared over h squared. And then I'm back to the same problem that I had before, actually. This is h squared over h squared. So now I have h squared minus a squared over h squared. And that doesn't get me that much farther unless I can recognize that this is h, this is a, and this is o, and this is a. So this squared plus that squared equals that squared. And so then that must be o squared. So that's actually, I thought I could get there, but I can't. So maybe I just have to leave that alone and work on this side. So let's work on the right side. On the right side, I have this is equal to sine x times cos x times tan x. Okay? And let's rewrite this as, well, sine and cos are already in the terms of sine and cosine. But then I'm going to multiply by tangent, which is sine x over cosine x. Okay? And now my cosines are going to cancel. Boom, boom. And then I'm just ended up with sine x times sine x. This is sine squared. And then I really have to be able to say, well, 1 minus cosine squared x, does that equal sine squared x? Indeed, it does if I use the Pythagorean identity. So I can use that down here by just saying, well, I can make this such that sine squared x equals 1 minus cosine squared x. So left side equals right side. I wonder how can I do that if I can't use this little trick. I think you need this little trick. I think you just need to remember that you can manipulate your identities to create something a little new. That one is just to write down our inverse operations there so that everyone can see very clearly. Subtract this cosine squared x from both sides. And that would give you a renewed version of the identity. Suresh?
So remember how you were saying on the left side that h squared minus x squared is equal to L squared?
Yeah.
You can just write that stuff down, right? And since you know that you have sine squared x, you know that that's opposite over hypotenuse. So
yeah, this is O squared over H squared. Yeah, but I still need to go through Pythagorean at some point. I thought, oh, this will cancel out when I find common denominators and stuff. These are fractions. I didn't need common denominators. So I was kind of ahead of myself there. But yeah, you can go through Pythagorean with opposites, adjacents, and hypotenuses. And actually reducing things to opposites, adjacent, and hypotenuses used to be my favorite way to do trig identities. But now I find it's easier just to express everything as sine and cosine. So that's what I teach. So here's a bigger one. Let's take a look at this one here. We have cosine theta over 1 minus sine theta plus cosine theta over 1 plus sine theta, and that's equal to 2 over cosine of theta. Okay? There's no way to make the right side simpler that I can see by looking at that. Maybe I could say that this is 2 secant theta, because then that would just put this on top, but that's really not any simpler. So let's express this side in terms of sines and cosines. We're actually going to do this addition over here. So I'm going to start by working on left side. And so I have cosine theta plus cosine theta. This one is over 1 minus sine theta. And this one is over 1 plus sine theta. Now, I am going to need to create a common denominator here. So just like when we were working with rational expressions, we want to take this as our denominator from this side. We can put these things in brackets to make sure that we don't make mistakes. And we're going to multiply this one by 1 plus sine theta, top and bottom. Okay. And we're going to multiply this one by 1 minus sine theta, top and bottom. That's going to be what we need to do to create a common denominator. Put them in brackets in both spots. Okay, now let's do these activities. So this is, we're working on the left side here. Now this is equal to 1 plus sine theta times cosine theta. So that's cosine theta plus sine theta cosine theta. That is this cosine distributing to that term and that term, doing both multiplications. This one gives me cosine. This is cosine times 1. This is sine theta times cosine theta. Okay. And then on the bottom, I have some rainbows to draw here. This is 1 times 1, and then 1 times sine theta. And then I also have to do sine theta times 1 and sine theta times negative sine theta. Okay, so I have to do all 4 multiplications there. So let's do that. And then we'll collect like terms, and we'll see that this is going to create a difference of squares. 1 times 1 is 1. Sine theta, 1 times negative sine theta gives me minus sine theta. And then I do sine theta times 1. This is plus sine theta. And then sine theta times negative sine theta gives me minus sine squared theta. Okay, and that's my common denominator. So I'm going to write that along over here. 1 minus sine theta plus sine theta minus sine squared theta. I'll get the same result over there because I'm multiplying the same two things. So that does indeed create a common denominator. Now let's do cosine theta times 1 minus sine theta. Similarly, I do cosine times 1 and cosine times negative sine. So this will be plus cosine theta minus cosine theta sine theta. Okay. Now we get out our red canceling pen of doom. And I notice that I have plus cosine theta. So that's 2 cosine theta. Those will collect as like terms. But here, plus sine theta cos theta minus cos theta sine theta. Doesn't matter what order I multiply these in, they're the same. So this is like plus 1 minus 1. So these two cancel. Okay. Then on the bottom, I have 2 things that cancel as well. 1 minus sine theta plus sine theta. Well, that cancels and goes to 1. So I just have 1 minus sine squared theta on the bottom. Okay, let's write another line. We're going to clean up our cancellations. So I have this is equal to cosine theta plus cosine theta. So that's 2 cosine theta on top. Okay. And then I have on the bottom 1 minus sine squared theta. But I already know something about 1 minus sine squared theta. If I know that sine squared theta plus cosine squared theta is equal to 1, then I can subtract sine squared theta from both sides to get cosine squared theta is equal to 1 minus sine squared theta. Okay, that is what I have down here. So it's equal to cosine squared theta. So let's write it that way. I actually prepared some extra page so that I could keep going. I think you are tight for page on there, so you may need to go on to your own notes. So this is equal to 2 times cosine theta over cosine squared theta. Cosine squared theta on the bottom cancels the cosine theta on the top. So this cancels that, and I have 2 over cosine theta. Over here, 2 over cosine theta was the right side. Therefore, the left side is equal to the right side. We are done. Equals right side. Therefore, left side equals right side. Didn't need that much extra paper. So therefore, there it is done. So just do the work, evaluate your fractions, create your common denominators, apply your fraction rules, and remember your new identities, and you will be able to complete the different practice problems that are on there. Other questions about this topic? So we could take down these ones as well, if you like, and we can take a look at them and prove them as identities as well. Again, as I was saying, this is the first time I've seen these two, and they are just variations of the Pythagorean identity. So let's prove them as though they were identities. And once we've proven them, then they are always true. So the first one is 1 plus cotangent squared x is equal to cosecant squared x. Move me out of the way. All right, let's prove it. The left side, let's simplify that. 1 plus, well, cotangent squared x. This is cosine squared x over sine squared x. Because cotangent is cosine over sine, whereas tangent is sine over cosine. So that's one of my quotient identities. Cotangent is equal to cosine over sine. Now I need to create a common denominator here. So I'm going to have sine squared x over sine squared x. That's 1. Plus cosine squared x over sine squared x. Notice that sine squared x plus cosine squared x is what we're going to have on the top, and that's equal to 1. So we have this is equal to 1 over sine squared x. Cosecant squared x, let's work on right side. We don't have much work to do. Cosecant squared x is equal to 1 over sine squared x. Why? Because cosecant is 1 over sine, so if I squared that, this would also be true. So they're the same. Now, if you ever encounter this, you could use that as an identity. To be honest, I would never spot that. I would always spot these relationships of sine squared x and cosine squared x. I see that one. I don't see this yet. Maybe if I work on a lot of trigonometric identities, I'll start seeing this and know that it's an identity. But for now, I'd have to prove it each time. Let's take a look at the other one. The other one, I believe, was tangent squared. Yeah, tangent squared x plus 1 is equal to secant squared x. Well, that one's going to prove in exactly the same way, and I'll show you. So here is tan squared x plus, what was it? Plus 1 is equal to secant squared x. Well, let's prove them as identities. So this is actually a good point where I'm just going to leave you. I'm going to leave you to solve that one, doing the same thing that you saw me do with this one. Okay, so let's make that smaller. We'll wrap up our video here, and I'll leave that one with you as something to prove. So now go ahead and work on the trigonometric identities that you have in your handout. Find your questions for me. If you have questions, ask me here, ask me by email, or ask me however you can find me. I'm pretty easy to find.